this extended system ID, if you remember situation yesterday, when we had two switches that were interconnected, and we had native VLAN 30 on one side and native VLAN 40 on the other side, and I told you, okay, this is now down because of the because of the port VLAN ID inconsistency. It's the per VLAN spanning tree causing this to go down, and this is how per VLAN spanning tree was able to actually detect what is the problem. Because here inside the bridge identifier we have this extended system ID, which is actually the VLAN identifier. So when the switch received the frame in the native VLAN that had this set, so on this untagged frame, so where is VLAN 10? There it is, VLAN 10. So this is untagged frame. We don't have VLAN tag here, so we just have the native Ethernet frame, and then we have the spanning tree. So here it received the VLAN identifier which didn't match the local VLAN ID. This is what causes this per VLAN spanning tree to say, oh, okay, sorry, I can't accept this because this is actually coming from another VLAN. There has been misconfiguration in the network. And this is the reason why I said, oh, okay, in order to show you this example when we have the mismatched VLAN ID, I actually have to run MST because I was running away from this problem. And this is how per VLAN spanning tree was actually able to detect that misconfiguration. But going back to my example here, and the reason why I was showing you this capture is this frame here, the standard spanning tree frame. So let's say that you have a task in your lab, in your layer 2 section, that says, make sure that you configure the link between Cat3 and Cat4, that it is 802.1q trunk, and that the native VLAN is 75. You know exactly what needs to be done. But what if they worded it, configure the trunk between Cat3 and Cat4 in such a way that 802.1d spanning tree BPDUs are sent untagged, that they are sent without tag, or that should I say that 802.1d frames are sent in VLAN 75? And you're thinking, hey, but wait, hold on a second, this is 802.1d that I'm running. But remember, this is not exactly true. What you are running is PVST. You are not running 802.1d. 802.1d frames are sent only in the native VLAN on the trunk. They are not sent in any other VLAN on the trunk. So basically what the task tells you is configure VLAN 75 to be native. So this is one example where they're going to describe a behavior of the technology without actually telling you what the technology is. So based on their description of the technology, or the description of the technology, you have to figure out what are they talking about. So they might tell you configure the native VLAN, straightforward, or they could tell you send 802.1d frames in VLAN 75 on this trunk, which basically tells you that this VLAN 75 on that trunk must be the native VLAN. So that's the reason why I went through the exercise of showing you why that little plus in the name, where is it? That little plus in the name here is actually significant. That signifies the support for 802.1d with these two spanning trees. The question is, what are the major differences between rapid spanning tree, per VLAN spanning tree plus, and rapid per VLAN spanning tree? Well, the major difference is that rapid spanning tree is the same as 802.1d in a sense that it is a standard-based protocol that Cisco supports only as a side effect. So when we have a traditional spanning tree, so I'm just going to call it the STP, and rapid spanning tree. These are standards, and STP is 802.1d. Now, interestingly enough, rapid spanning tree was originally 802.1w, but it's actually now 802.1d-2004. These are the standard-based. Now, Cisco supports this with that plus thing. Now, you cannot configure these modes as the only as the only spanning tree modes on your switch. You can only support them through the rapid per VLAN spanning tree or per VLAN spanning tree plus. Or with MST, MST also has the backwards compatibility with them. But you cannot run this mode on the switches. Now, the major point about these is that there is one instance. Oops, I need to learn how to spell actually at one point in my life. It might actually help me a little bit. So there is one instance for all VLANs. So with these traditional approaches, there is no support for multiple VLANs. That was never envisioned by the spanning tree. It has been addressed with the multiple spanning tree, but in order to address the need to maybe have different topologies for different VLANs, Cisco invented per VLAN spanning tree and rapid per VLAN spanning tree. Now, they're basically behaving in the same way as spanning tree and RSTP do, except there is one instance for each VLAN. But in order to accommodate this solution, Cisco used a proprietary destination MAC, which made it incompatible with spanning tree and rapid spanning tree. So this is where that plus comes into play, and where the compatibility is actually provided through that plus. So basically, on Cisco switches these days, you do not have PVST. You have PVST plus and rapid PVST plus. Now, IEEE realized that their approach, that one instance to rule all the VLANs or one ring to rule them all, is not exactly the best approach. So they looked at Cisco's solution, which was to run one instance for each VLAN, which is also an overkill. And let me show you why is it an overkill. Now, let's say that we have two switches. So this is switch 1 and this is switch 2. And we have two links between them. Now, as we know, one of these links must be blocking. And let's say that we have 10 VLANs here in our network. How many possible logical topologies we have based on this one physical topology? Well, we have the logical topology in which the top link is operating and the bottom link is blocking. And we have a possible logical topology where situation is reversed, that the top link is blocking and that the bottom link is forwarding. So we basically have two logical topologies that are possible. But with 10 VLANs here configured with PVST, we are going to have 10 logical topologies created, because that's basically what the spanning tree instance is. It's a logical topology based on the same physical topology. So basically, we are creating 8 more. We are creating 8 more than we need to actually address the capabilities of this network here. So this is why when IEEE were trying to solve the problem of multiple VLANs with the spanning tree, they realized that Cisco's approach is actually on a completely different end of the spectrum of possible capabilities. You have one ring to rule them all and one instance per each VLAN. So MST is basically something that sits somewhere in the middle. This is the way I like to think about it. Of course, MST is much more complex than this, but this is the best way to approach it if you feel uncomfortable with MST. And in my experience, every single network engineer feels uncomfortable with MST. So with MST we have is we have VLAN instance, or actually how should I word this? We have VLAN to instance mapping, which basically tells us that we can map multiple VLANs to one spanning tree instance. So if you take a look at this problem with the eyes of MST, what we can have here, so let's say switch 1, switch 2, again, we have two possible topologies, right? One, well, let me just not repeat that text, so I'm just going to draw them up. So, clone this once, clone this second time, there we go. So, one possible instance is this, and the other possible instance is this, one possible logical topology, right? So basically what we have here is that our 10 VLANs we can map, for example, 5 VLANs to instance 1 and 5 VLANs to instance 2. That means that if we create this as the root for instance 1 and this as the root for instance 2, we are effectively going to be using both links in our topology with 5 VLANs using one link and 5 VLANs using the other link. So we don't create 10 instances like we did with per VLAN spanning tree, but we create only 2 instances that we need. And mind you, I have simplified things a little bit. I mean, if you create instance 1 and instance 2, you will actually have 3 instances in your MST because there is the mandatory instance 0, which by default has all VLANs mapped to it. Now, you can run MST with no VLANs mapped to instance 0, but you will still have the instance 0 configured. So the better approach here would be to actually use instance 0 and instance 1, and that this is, for example, the root for instance 0, and that this is a root for instance 1, but I was simplifying things there so that you can understand what the major differences, what fundamental differences between these spanning trees. Spanning tree is one of those protocols that is much more difficult to understand than actually configure. The configuration of spanning trees can be really not doing anything because it's already configured for you, it already works, it's a very, very simple protocol in the way it operates, but sometimes you may need to make certain decisions. You may need to make some changes in your spanning tree configuration to make it work according to the requirements. So one of the important things is the root election for the spanning tree. Now, the root election is influenced by 2 things. One is the priority, and the second one is the MAC address. Now, I should say that this is actually bridge priority, and that this is a bridge MAC address, which together form something that is called bridge ID. This is a composite value where we have priority followed by the MAC address. So priority will actually take precedence over the MAC address. But when we talk about the MAC address, it's important to know which MAC address we are talking about. Now, on our 3560s, you are going to have 2 gigabit ports, and you are going to have 24 fast Ethernet ports. Now, the MAC address that we are talking about, the bridge MAC address, is actually none of these. It is the one MAC address below all of them. It is the system MAC address. So I'm just quickly going to show you this. So here I have my Cat3, and if I take a look at show interface gigabit 01, this is the MAC address on this interface. And you may remember that I mentioned that this is the lowest interface we have on this switch. Now, if I take a look at show spanning tree VLAN 10, I will see here that my own bridge identifier, so this is the bridge ID, this is my own value, this is the roots, these are the root values, these are my own local values. So I can see here that the address says 0019 matches, 060C matches, 6100, and you can see here that 6101 was the lowest address on my system. Now, you can easily find out what is the system MAC address that is in use, and you can see that with show version. If you type show version, you will see it here. It will be displayed, just one second. It will be displayed here as the base Ethernet MAC address. So this is the value that will be used for your bridge ID. And you can see here that this one does match. It's 6100. But you know, you have to praise Cisco's consistency in displaying the MAC addresses. So in iOS, they are displayed with dots in between, and here they are displayed just like in Windows. I just love that consistency, especially helps with copy pasting those values if you ever have to do them. So that's the MAC address that will be used to actually determine who the root is, not any interface MAC address. Now, the priority is the value that you can set yourself. The possible values are from 0 to, what is the maximum value? I don't remember. Let me take a look. I think it's 65,536, but not entirely sure. So I'm just going to say spanning tree VLAN 1 to 4094, question mark, priority, question mark. Well, it's 61,440, okay? But technically speaking, the maximum value is 65,536. But let me explain why you cannot actually enter this value. Because these values here need to be increments of 4096. So you cannot use any values in between. So it's 4096, 8192, 12,000 something, 16,384, etc., etc., etc. Now, the reason for this is the third bit here. It is the extended system ID. Now, you've seen that already in those captures that I did, and you can see it here as well. If I do show spanning tree, you will see here that it says, let me see, it says priority. Now, actually, it's more obvious here. So this is my local value. This is VLAN 1. It says my priority is now 32,769. But it's not 769. It is 32,768 with the extended system ID of 1. In VLAN 10, my computed priority will be 32,778, which is really 32,768 plus the VLAN number. For VLAN 20, it will be plus 20 here, but this is actually this plus this. Now, the way this is carried inside the actual BPDU update is that what we have for priority is actually a multiplier for 4096 followed by the actual value of the VLAN. So this is why we cannot enter any values that are not in between 4096, because we can have 4094 VLANs. So when we set priority 0 for VLAN 4000, for example, what we are actually setting is the priority 4000 that will be calculated. If we do the same thing for VLAN 1, we are actually going to be setting priority 4001, and so on and so on. You get the idea there, I hope. So this is the reason why we cannot set the priority to any value we like. We can set it only in increments of 4096, and then based on which VLAN this is used in, the priority will be slightly adjusted based on that information. Now, for some other vendors that are using the traditional spanning tree, the vendor that is called Juniper comes to mind, there you can actually set the priority to any value you like, because there is nothing in the specification that prevents this behavior. So this is a very, very Cisco specific behavior, but you know what? It's perfectly fine. It doesn't matter that Cisco does it this way. It is even going to be somewhat compatible with other vendors. Now, these are the three things that influence the election of the root. So I should really say that these two are really the same thing. Now, in the lab, they might ask you that a certain switch needs to be a root, or that a certain switch must not be the root. So let me give you one interesting example. So we are going to have our 4 switches. So switch 1, switch 2, switch 3, switch 4. And they are interconnected like this. So let's say that this is switch 1, switch 2, switch 3, and switch 4. And the task says, oh, let me add the crosslinks as well. So the task says, make sure that switch 4 is never the root. So switch 4 must never be the root. Well, you're looking at this example and you are thinking, okay, before I proceed, let me say that there is a host connected to each of these switches. And let's say that we are talking only about VLAN 1. We don't care about any other VLAN. So this is just VLAN 1. So this is the setup you have. And you are thinking to yourself, okay, how do I solve this particular problem? Well, one possible solution is set the priority on, let's say, switch 1 to 0. Let's set to 4096 on this one. Let's set to 8192 on this one. And let's set it to 61,000, well, like whatever the maximum is. So let me just, actually, what was that maximum value that we had? It was 61,440. So, okay. So this one here is 61,440. And what's going to happen here, effectively, this will be the root, this will be the secondary root, this will be a ternary root. But what happens, for example, if these links here fail? So now switch 4 is cut off from the network. Who is the root in the network? Well, in this network here, R1 is the root. But in this network here, switch 4 is the root because it has the lower priority, the lowest priority of all devices in this network. This is just a host. This is not a switch. So have we satisfied the requirements of our task now? Not really. So let's go back to the drawing board. Let's try another possible solution. Now, there is an advanced feature in our spanning tree, which is called the root guard. Now, what root guard does is it can be configured on the interfaces. And if we receive a BPDU that is called a superior BPDU, and superior BPDU is the BPDU that is better than our own, better than the BPDU of the current root, if we receive this kind of BPDU, we are actually going to block that port. So we can use that feature and configure it on this interface here, on this interface here, and on this interface here. Which basically means if switch 4 claims to be the root, we are actually going to disable the port facing switch 4, and we are going to isolate our switch 4 from the rest of the network. Perfect example. Or perfect solution, I should say. This link fails, and this link here fails. Now, let's see what happens here. Again, our network is now very, very different than it was. Switch 1 may be the root. So let's say that we made sure that switch 1 is the root. Now, switch 3 lost the BPDU it had on this interface here, and lost BPDU it had the interface on this here. So the only valid BPDU it will be receiving will be a superior BPDU arriving from switch 4. Mind you, the BPDU that originally arrived from switch 1. So it's not switch 4 now claiming to be the root, it is still switch 1 claiming to be the root, but we are receiving a superior BPDU on this port, and we are going to start blocking it, effectively cutting off switch 3 from the rest of the network. So this is not a good solution either. So let's take a look at another solution. Now, given these two scenarios that we just went through, the only valid solution is to turn off spanning tree on all switches. So we're going to turn off spanning tree here, going to turn it off here, going to turn it off here, and we're going to turn it off here as well. Now, the problem with that is, of course, that we are going to end up with a horrendous loop in our network that is probably going to crash these switches very fast. So none of the solutions for this task are correct. Now, and here I'm going to zoom myself in. This is where you are going to end up when you are ready for the lab. You're going to look at a very easy task and you're going to way overthink it. You're going to think, oh, so what happens when this link fails? What happens if this switch does this? What happens if this link fails? Oh my God, oh my God, oh my God, what is the actual solution for this? Don't do that to yourself, because this is the most dangerous example of overthinking the problem. The correct solution was just in this network, when everything works normally, just make sure that Cat4 is the least preferred to be the root. So basically our first solution was correct. Our second solution was also correct because we are really preventing it from becoming a root. Now, if 3 links or 2 links fail in our network, yeah, it may lead to some results that we didn't really want to have, but that's okay, right? Because that's not really what the task wanted. They just wanted to see, do you know how to influence the root elections? So don't do that to yourself, that you are way overthinking the problem, the way I did right now. So this is a typical example of a student who is ready for the lab and he knows the caveats, or he or she knows the caveats of the technology, understands the dangers of different technologies, and then goes through the motions of overthinking the problem to the point that no solution appears to be correct. Yet, he needs to do something. There needs to be a solution implemented there. So again, going back to advice that I've given you a couple of days ago, is go with the simplest, most straightforward solution you can think. That's it. The most simple solution in this case was just lower the priorities on 3 other switches and make sure that our switch 4 has the highest priority of them all, or use the root guard. The next thing that I'm going to talk about is going to be making sure that you influence certain decisions made by the spanning tree. So again, I'm going to use very simple example of just 2 switches. So I'm going to use my switch 3 and switch 4. And this is port 23, this is port 24. Oh, sorry, my bad. This is actually also 23. This is 24, and this one here is 24. Now, we already configured switch 4 to be the root. Given all the default values otherwise, what will be the actual spanning tree topology that we are going to end up with? Well, port 23 would be a designated port, port 24 would be a designated port, and as such, they would be forwarding. They are going to be designated ports because these are the ports on the switch 4, which is the root, and their cost to reach the root is 0, and there cannot be lower cost than that. Now, more interesting situation here happens on switch 3. Their cost to reach the root is the same. In this case, if you're using traditional spanning tree, it would be 4. So we have, oh sorry, I should be careful what I'm saying, it will be 19. So the cost will be the same to reach the root. So we have to go to another tiebreaker there, which would be what is the port priority on the other side. The port priority on the other side is the same, it's the default value because we haven't actually changed it to anything. Then we are going to make the determination which of these ports is going to be forwarding based on the port ID. And in spanning tree, the lower value always wins. And we remember that port ID 0 will be gigabit 01, and then from that on, we know that 23 will be lower than 24. So our situation here is that this is going to be the root port, and as such, it is going to be forwarding. This port here will be actually blocking. Now, iOS will tell you that this is an alternate port. Now, this alternate port is actually something from rapid spanning tree naming, because alternate port is a standby port for the root port. Should the root port fail in rapid spanning tree, the alternate port can immediately be promoted to become the root port. In traditional spanning tree, or when you're running per VLAN spanning tree plus non-rapid one, this cannot happen. We still have to go through the through listening learning phases before we can actually start forwarding. So let's see if this is true. So on Cat4, I'm going to say show spanning tree VLAN 10, so here, oh, let me bring up the Fastnet 23 interface. I'm just going to configure it in the same way as my Fastnet 24. Okay, now when the interface comes up, we may need to wait a little bit for it to come up, because now it's in listening, so we are not going to see it in forwarding state just yet. But let's wait for that to elapse. And to wait for that, we need to wait forward delay time. We are going to spend listening. Then after that phase is done, we are again going to spend forward delay time in learning phase. We should be there by now. So we are now in learning phase, where we are going to spend 15 seconds. And after that elapses, we are going to move into the forwarding state. So now we can see that on Cat4, the switch that is actually the root, both of the ports, Fastnet 23 and 24, are designated forwarding. And we have here the cost on these interfaces is 19, but that's the cost of that interface, not cost to reach the root. On Cat3, if I do show spanning tree VLAN 10, I'm going to see here that Fastnet 23, as expected, is the root port that is forwarding, and Fastnet 24, as expected, is blocking port, and we can see it's actually an alternate port. Now, mind you, this does not take effect right now because we are running per VLAN spanning tree. This alternate will have special meaning only when we are running MST or rapid per VLAN spanning tree. So this is the situation that we have right now. But let's say that the task told you that what we need is actually a slightly different situation, that we wanted to have, let me just delete these things. Like so. So let's say that the task said that what we wanted to have is this, of course, designated forwarding. There is nothing we can do about that. But that we wanted to have this as the root port, and that we wanted to have this as alternate blocking port. And by the way, do not make any configurations on switch 3. So the only place where we can make any modifications will be switch 4. So how to do that? Well, there are two values that we can manipulate to make this decision. We can either manipulate cost, or we can manipulate port priority. Now, cost affects local decision, and priority affects remote decision. So in our case, what we need to do is we need to have switch 4 somehow influence the decision made on switch 3. So in this case, the correct solution would be to actually use the priority on this port here. What we need to do is lower the priority on Fastnet 24, or we need to increase the priority on Fastnet 23 to make this port less desirable than this one here. So let me show you this. So I'm going to go back to my terminal, and on interface Fastnet 24, I'm going to say spanning tree VLAN, and again, this is per VLAN thing if you're running per VLAN spanning tree. So let's just make this for VLAN 10. So I'm going to say spanning tree VLAN 10, port priority, and the default value is 64, or actually is 128. So in this case, let me make it, let's say 256. Oops, what is the maximum value I can do? 240. Okay, let's set it to 240. So if I go to Cat3 now, if I do show spanning tree VLAN 10, this will take just some time. Come on. Did I actually do it correctly here? Do show run interface. Fastnet 24. This is, Sorry. I actually need it the other way around. I need to make FastInit24 lower priority, not higher. So I made a complete mess here. So let me just set it to something lower than 128. So now we should be seeing here that the roles have actually been reversed. This is how it was before. We can see FastInit23 was root forwarding and FastInit24 was alternate blocking. And here now we can see that FastInit23 is now alternate blocking, so that happened immediately, but this one cannot transition directly into forwarding. Even though it used to be alternate port, remember, this takes no effect for traditional spanning tree for 802.1d or for per VLAN spanning tree. So this port is now a root port, but it needs to go through the listening, learning, and only then goes into forwarding state after it has spent forward delay time in each of these intermediate stages. So this is now the situation. So this is one way of solving this task. Now let's take a look at a similar example. So I'm going to use the same topology, but now let's say that the task says you are not allowed to make any changes on switch 4. You need to make changes on switch 3 to reverse the role. So I now want Fast Ethernet 23 to actually be forwarding. And I want this one here to be alternate blocking. So I want to reverse the change that was made here. What I need to do here is manipulate the cost, because cost here is the local decision. So let me just copy this to save me the time from typing it. So I'm going to say paste here. So what I need to do is actually manipulate the cost to reverse the role. Because remember, cost, the local decision, will always take precedence over a hint from the remote side. So going back to my terminal, this is the situation I have now. So take a look, the costs are equal right now. So what I'm going to do is I'm going to go to FastInit 23 and I'm going to say spanning tree VLAN 10 cost, let's make it 15. So now if I do show spanning tree VLAN 10, I will see that the roles have started reversing again. So here I see that this is now a root port. Again, it needs to go through the motions of listening and learning, and only then can go to forwarding. But FastInit 24 has immediately changed state to blocking. And also a note, this priority here shows us the local priority. If you want to see the designated ports priority, what you actually have to do is show spanning tree interface FastInit 23 detail, and here in VLAN 10 we will see that the designated port ID is 128.25. So this is showing us the remote port. But let's take a look at for Fast Ethernet 24. Here for VLAN 20, here for VLAN 10, we are going to see that the designated port ID is 3226. So this is where we are seeing the port priority of the remote side. Also take a look that this is identified as port 26. FastInit 24 is seen as port 26, not as port 24. Why? Because we have two other ports that are above 2 gigabit ports. The question that I got is, are any MAC addresses lost during the link swap? Well, whenever there is a topology change in spanning tree, different things happen with the MAC address table. When you have a direct link failure, that means that the link that was connected somewhere has lost connection, so that goes down. All the locally learned MAC addresses from that link are immediately flushed from the MAC address table on the local switch. Now, when you have an indirect link failure, when there is a swap like this happening, what is going to happen is that let me show you this, that the aging timer, which is 300 by default, is actually cut to, I believe, oh my God, I can't remember this, but you know what, we can test it. So what I'm going to do now is I'm going to go onto my switch, so into FastInit 23, let's change the cost here back to 19. So if I do show spanning tree VLAN 10, aging timer is actually going to be set to the forward delay. right? So they're not aged out immediately, but they will age out much, much faster. So remember here that we had, oh, I actually deleted, but we can see it for VLAN 1, for example. For VLAN 1, we can see that the default aging timer, so this is the MAC address aging timer that controls how long the MAC addresses stay in the MAC address table, is by default 5 minutes. But when there is an indirect topology change, it will be set to the aging timer of 15, I believe, for the duration of the max age. But this has been a little bit longer, or maybe no, yeah, it's about that time. So we can see now that it reverted to 300. So there is no immediate, well, it depends what kind of, what caused the switchover, right? In this case, it was a soft event. So when it's a soft event, they're not going to be immediately aged out. But if it was a hard event, for example, link going down, all MAC addresses from that link are immediately flushed from the MAC address table because they're no longer valid. We have to relearn them. But keep in mind that on the switch, flushing the MAC address table is not a catastrophic event. It happens all the time. I mean, it's not catastrophic in a sense that the traffic will not be impacted. The traffic will get where it needs to go. But for the duration of the learning, while the switches are actually learning where the MAC addresses are, you might have some unnecessary flooding of the traffic. So it's not a catastrophic event, but it could cause bandwidth strains depending on the traffic volume that you have in your network. But you're not going to be losing any traffic when the MAC addresses are aged out. That's the whole idea of the switches. They are transparent switches. They are sitting in the traffic path. They are forwarding the traffic, but they are not actually going to drop the traffic if they don't know where to send the traffic. They will, when they don't have a MAC address learn, they are, instead of dropping the traffic, what the routers will do with the unknown traffic, the switches will simply flood it out on all the ports in that VLAN. So yeah, you might have some unnecessary flooding of the traffic, some bandwidth use increase in your network, but the traffic will get where it needs to go. So yes, there will be an event involving the MAC address table, but it will not be catastrophic for the. Okay, another question that I got was, what happens with the traffic on the link during the time of the switchover? Well, let's take a look at the switchover. So if I go to the switchover here and let me again cause it, oh, oops, interface fastnet 23, let me again cause it to change. So if I do show spanning tree here, I can see that port 23 is root and is listening. That means no production traffic is going over this link. And fastnet 24 is blocking. That means that right now, effectively, there is no traffic going between Cat3 and Cat4 other than spanning tree. There is nothing, well, spanning tree and CDP and VTP still operate, but nothing else works. So there is no transit traffic that goes. And just to test that, let's add on both of them. So I'm just going to say interface VLAN 10 IP address. Going to add an IP address there, and let me go to Cat4. Yeah, I know it's a duplicate address. So now from Cat3, I should be able to ping Cat4, and that works like a charm, because show spanning tree shows me that they have actually converged by now. So I can see that this is root forwarding and this is alternate blocking. But if I go to interface fastnet 023, so let me start ping from Cat4. So I'm going to start very long ping. So if I go here and I say spanning tree cost 19, so now show spanning tree VLAN 10 shows me that these are now converging. I can see that now I no longer have ping going on until they converge. Now 1000 pings went much faster than I was hoping. I thought it was going to go so that we can actually see the drop in that original output, but this is fine as well. So now while the spanning tree is actually converging on Cat3, there is no traffic. So now we are learning the MAC addresses, but learning the MAC addresses still means no production traffic. Now we have switched to forwarding, and now we can see that the traffic has actually gone through. And this is one of the reasons why we have rapid spanning tree, because rapid spanning tree in this particular case would instantaneously switch to forwarding, because that is what happens with root port. So let me change this to be rapid on both sides. So I'm just going to say spanning tree mode rapid PVST. So now when I do show spanning tree VLAN 10, I can see that spanning tree, that spanning tree is enabled and that the protocol is RSTP. And I can see pretty much the same situation right now. So let me now switch over. Let me start the ping from this side. But this time I'm going to be a little bit smarter than that. Okay, so I'm going to go to interface fastnet 23 and I'm going to change the cost here to 15. If I do show spanning tree VLAN 10, I can see that the switchover was instantaneous because this is now root port and is forwarding. And if I go here, and there it was. So this is where the switchover happened. Right? It's very, very difficult to spot. Yes, there was maybe minor loss, but maybe this was just unfortunate timing because this happens very, very, very quickly. So this is what was the result of rapid spanning tree switching over, right? Much different than what we had with the traditional spanning tree.